I'm John Rose, and one of the merry Oracle Java team, and Brian and Mark and I and all the other folks have been working pretty hard on our big job, which could be summarized as keeping Java vibrant. It's very exciting since in the last several years that we've been given both the resources and the motivation to go do some really cool new stuff with Java, and I think you've all seen the results. So it's later on in the conference, and you've already seen some presentations about what Valhalla just now, and AOT, and var handles, and Panama. So there's a lot of specific, very well-designed projects underway. I am going to give you more of a sort of a crazy future-leading collection of thoughts, not all of which connect well. I'll tell you, when people ask me what I do, I have to think for a long time because there's a list of about 20 things that are happening at any one time, and you're going to enter into that sad personal world of mine of too many interesting problems to worry about. So in preparing this talk, I felt a little bit like the donkey between two equal piles of grain, or maybe 50 equal piles of grain, or maybe a dog in a park with too many squirrels. But here we are. I'm talking about bytecodes and, by extension, bytecode architecture, and we'll even have a chance to talk about what the future of the VM ought to be over the next 20 years. But in fact, none of what I say about the future is intended to outline our general product direction, etc. So you'll have to read that slide, and if you want to go have a coffee break now for the next 45 minutes, it's fine with me. But for hypothetical purposes, I'd like to talk about the instruction set architecture that we have, our beloved bytecodes, our challenges, and what we might be doing in the future. I want to look again at the basics to try and understand fundamentally what our JVM is doing, to point out some of the sharp corners in what it's doing today and the design thereof, to sketch some future fixes perhaps. And some of this is overlapping with a talk I gave at JFocus. There is a link to it. That's about, again, JVM challenges for the future. But today I'd like to dive deep into bytecodism, since we're talking about new kinds of bytecodes and new kinds of polymorphism. So last year, this was an image that captured my sense of what the VM feels like. And it's useful, right? Most of the pieces on that Swiss Army knife, like most of the pieces of the bytecode engine, our JVM, are useful, but there are some pieces in there, like maybe the toothpick that you don't use very much, and maybe there's also let's see, JSR ret or multi-ANU array or something that kind of, you might think of a way to use them, but they don't come up very often in your thoughts. The VM Vision from last year, just as a reminder, this is directly from Brian's and my talk, is let's find some pain points. Let's find some rough edges where the VM doesn't quite do what you want from a language point of view. And you know, in the last year, we've only gotten much more ambitious, at least in Java per se, what we want to do with the language and the VM. We've got a lot more crazy requirements for polymorphism from Project Valhalla, and value types will up the ante even further. So we have more pain points to think about. So there's an update on that problem from last year. So let's talk about the design of the VM. What is in the VM? This is, for most of us, motherhood and apple pie, but I thought I would go over it anyway. It's a way of working with data and code in a way that is perhaps more unusually safe and portable, right? So you can run everywhere and you don't crash. And let me unpack those concepts in detail. Data structures in the JVM are connected by managed pointers in a managed heap, and there's dynamic typing as well as static typing. So there's a sort of suspenders and belt. We get both primitives and objects. The code does run fast without pre-processing. It's directly executable, but it also amounts to something like an abstract syntax tree that you can compile. The binding is done lazily, so that you have just one binding decision instead of a compile time binding decision, which might go out of date. This is, that's the C++ way. With Java, you have to pay the cost at runtime of binding. The safety is based on enforcing types, and also as a layer above that, enforcing access control rules, public and private and so forth, and it has proven over the years fairly robust and secure, although not impervious to all attack, but that's a serious value that we continue to uphold. We don't want either erroneous or malicious code to take down the system. And finally, the portability is kind of cool because it means, and it's part of the reason that I'm here today to talk about changes to the VM, because we continue to aspire to run the VM on whatever important architectures are out there that in the hardware that people want to run their apps on. So that's Intel and Spark, of course, and ARM, PowerPC, you name it, we want to run it. And that also means whatever the hardware designers have been inventing, I see some Intel people here, we have to keep up with that too, because some of that stuff isn't directly expressible in Java yet. Okay. What are the clever moves we have? GC, obviously. Primitives with boxing interoperating to objects, that's cool. The code is the JIT compilation, which I already mentioned. The profiling is something neat that the VM can do online profiling to then do behavior directed re-optimization of code. 20 years ago, this was all pretty new stuff, right? But now we depend on it every day. It's the redundant checks, like in the verifier and in the language compiler. The fact that abnormalities cause, hopefully, exceptions to be thrown rather than bad code to run silently or crashes. Those are clever moves in the VM. And one of the reasons that we are so portable is at the very beginning of the Java ecosystem, some very clear thinkers put together the specifications to say exactly how our system was going to work. If you compare our specifications with others, there is often a difference in quality, and this gives us the ability to continue to evolve the implementation with respect to the spec as opposed to with respect to yesterday's implementation. In keeping with an upcoming theme of complexity, I would say that although there's a lot of complexity in all those clever moves, they're best when they're invisible. And so it used to be people would say, well, I really can't get with this garbage collection stuff because there's all this complexity going on under the covers, and I don't trust the machine, and I can do a much better job managing my malloc blocks, right? You've heard people say stuff like that, maybe. But in fact, a lot of people have gotten used to trusting the insides of the VM, although, of course, it's always a give and take, and many people in this room have cursed the garbage collector and found ways to work around it. But still, the majority of uses of the JVM's GC are treating it as if it were a simple entity, when in fact it's not under the covers. So complexity hidden can be okay. So how are we doing today? Is our data easy to understand? Is it compact? Is it flexible? Yes, partly. No, partly. Does our code continue to efficiently encode what we want to do and run fast and flexibly? Well, yes, but perhaps not on the data structures we want today. Are we still safe? Are there no sharp edges? Mostly, yes. Let's keep that true as we evolve the language and the VM. Are we still portable? Yes, and let's keep it that way. But I want to probe what the weak spots are on each of those points too. Our data has too many pointers in it. I'll get into this in more detail later. Our genericity is weak, so as Brian has pointed out, it's hard to tune a data structure. You can't write an array list of int the same way you can do a corresponding C++ template. We're going to fix that. And probably the worst thing about Java data of all time is that it's terribly racy. Java introduced threads and multiprocessor programming, but we also introduced by default mutable data, which is kind of painful.
Did you say terribly racy or terribly racy, or both? Terribly or terribly, as in tearing?
Oh, yes, yes. Tearingly racy, yes. Yes, we're on a tear with racing. Thank you. As was just mentioned not a half an hour ago, our compilation unit size is a little bit limited. Our 16-bit limits, why would anybody want more than 16 bits, right? Our compilation unit, the class file format, is also a little bit too Java specific for the kinds of workloads that we might want to run in the future. Are we safe? Sure, we're safe until the next earthquake hits, but the hotspot code base in particular is highly complex. That's just, that's what we throw a lot of our engineering time at, is maintaining that code base and trying to understand it and keep it sane. And what could go wrong with portability? Well, I would pick our arrays and our primitives are now too small, and our threads are too big. Those are our two biggest portability problems. I'll have more to say about that in a bit. So, gee, that's all painful, right? So let's remember, though, that Aeschylus, did we already have an Aeschylus quote today? He says that suffering makes learning. Gain through pain. So we're going to blunder around. We're going to step in the puddles and look for stuff and hopefully find stuff as experimentally as we can. This is the slide verbatim from last year, just to review, showing some of the pain points. In particular, the var handles here are mentioned as upcoming projects. You've seen an update on that this week. And then there's some stuff about arrays 2.0. I'll be talking more about that. Brian just told you about parameterization and value types. You've seen presentations on FFI. So most of what's on this slide you've been refreshed on already this week. But I want to talk in particular, I want to do a deep dive with thanks to Attila, from whose earlier presentation of earlier year talked about bytecodes and why there are so many. I'd like to go there too. Do you know where this quote comes from? Programming languages should be designed not by piling feature on top of feature, but by removing the weaknesses and restrictions that make additional features appear necessary. I think it's either Sussman or Steele. I think it's on the revised report of the Scheme algorithmic language. Scheme, in particular, they claim, and I agree, demonstrates that a very small number of rules, akin to the rules of chess or of even Go, for forming expressions with no restrictions on how they are composed, suffice to form a practical and efficient programming language that is flexible enough to support most of the major programming paradigms in use today. So, as with Java, Scheme has a certain ability to be both object-oriented and functional and imperative, and it does so with a small number of moving parts, relatively. So this applies to VMs. Virtual machines, I claim, should be designed by removing the weaknesses and restrictions that make additional features appear necessary, right? So I sandbagged. This is not really a talk about adding new bytecodes. It's a talk about removing old bytecodes. So an ideal VM would demonstrate that a small number of rules for loading programs, which, a class file is an expression that you hand to the expression evaluator, which is your VM. No restrictions on how they're composed should suffice to form a good platform to support most of the major programming paradigms. We're not doing a fully ideal job here, but we can learn from our aspirations. So here are the Scheme fundamental operations. Names and constants, of course. You can call a function. You can create a function using a lambda expression, which we're all familiar with in this room now. And you can define a name to an expression. That's all there is. That's all you need. Of course, there's some library functions, but there aren't any other primitives. Not even if then else needs to be a primitive, right? It can all be expressed with lambdas. You, of course, need lexical scoping.
Shift reset.
Shift reset, yes. Well, I'm not going, yes. Not going to the coroutines yet. There is assignment also, so Scheme actually has an impure side effect mechanism in it, so there it is, just like Java. Control flow is, here's a complex expression that in terms of lower level constructs, here I'm not supposed to point into there with my finger, I'm supposed to use a laser pointer. You'll see that this complex expression, if you work it out, it does the same thing as this if then else. So the if is just a syntax sugar for this underlying library function, which is a three-way question mark colon by value selector that picks one of two lambdas and executes it right away. And if you know Smalltalk, that's how Smalltalk does if then else, also with a pair of blocks. And here's a pair of lambdas. Everything else is syntax sugar. A scheme purist will say that there are certain things a scheme purist already did say that there are certain things beyond this model, but that's basically enough for our purposes today. So you might build a bytecode engine for scheme, and if so, you might have bytecodes like this. This is from, everybody does a scheme at some point in their life, I think, and this was mine. My bytecodes actually happen to be literal capital letters of the alphabet, so I could read my bytecodes. So there you can do a perfectly respectable and somewhat rich scheme engine on top of 16 bytecodes. Not bad. Actually, a few more. There's a couple different branches. Okay, what about Smalltalk? It has a similar set of fundamental operations. Function return is a special operation, unlike scheme. Blocks and objects are a little different, but you make objects by calling library functions. So object creation is not a subprimitive, a primitive of the language. There is assignment also. Everything else, again, is a library class or a method. So if you go to a Smalltalk VM, you get to press the button until the slide goes. You get a few more operations because the object model is a little bit richer than Scheme's function model. But many of these operations will look familiar either in comparison with either the Java virtual machine or the Scheme virtual machine I just showed you. There's a funny line number annotation opcode here. This is the GNU Smalltalk engine, which I picked at random. But yeah, there's push a global, push a constant, push one of my fields, that sort of thing. Actually, you send yourself a message to get a field. So Java fundamental operations. These look familiar too, right? But wait, there's more and more and more. There's a lot of Java fundamental operations. The language feels reasonably workable and it feels simple even to a student, but in fact, if you analyze it, it's got a lot more than either Smalltalk or Scheme, and therefore, the VM is similar in complexity. Here's a number of bytecode points that's similar to the previous charts, but we haven't even gotten out of data movement. Right? And I'm including the first part of return as data movement instruction here. So, oh look, there's the array bytecodes. Yeah, okay, there's another whole block worth another small virtual machine worth. Maybe array bytecodes are Turing complete, I don't know. And then there's some other miscellaneous ones. The top group here is the control flow thingies plus comparators. So there's a miscellaneous bundle of control flow operations, some of which are obsolete, others of which are macros for smaller ones. And then the lower frame here shows all of what I call the nominal instructions, the instructions which take as a parameter a name that must be linked. Right? So anything that refers to a class by name or a method by name or a field by name is a nominal instruction. These nominal instructions in the Smalltalk engine in the Smalltalk framework would correspond to message sends, right? Just one kind of instruction instead of however many there are here. And then of course there are all of the primitive operations plus a few miscellaneous like monitor, enter. And I also like to think of method entry as an implicit instruction at the beginning of every method. It's the one that sort of unpacks the incoming arguments into locals and also does a monitor enter if necessary. Okay, so and this list doesn't fit on the slide, but we all know what it is, and it's all very regular. All right, so what can we do to simplify? Well, there's a bunch of moves we can try, and I want to comment on them. Some of them we want to do, and others we can't do or don't want to do. But of course, what
what about those prefixes? Do we really need all those prefixes? Well, yes, they're a nice optimization. But Brian just showed that you can write perfectly reasonable code without the prefixes per se and put them on later on, right? You have a type parameter that says what kind of a value it is, but it's deferred, and so you use some sort of other prefix like vload, vstore, or qload, or I don't care what your variable, what the letter is, but use something else, and then later on, if you want to, you optimize it back to an iload or an lstore or whatever. And eventually, these instructions could, in principle, become part of a deprecated or a second-tier instruction layer that you don't really need in practical purposes. They become quickened bytecodes inside the VM, perhaps.
Here's the dynamic language use case as well.
Yeah, there's great dynamic language use cases. And then return becomes you have a v return. Maybe you have your pop and pop2 guys. They have to negotiate whether you're a slot pair or not. So maybe do something funky with stack instructions. The effect of this is that every local value syntactically within the bytecodes looks like an any. Any in the sense of the Valhalla any parameter. So you can, if you wish, syntactically, and sometimes it's useful, compile your strongly typed programs to use type parameters for their types. I do emphasize that strong typing is still in play, except perhaps for the use case of intentionally dynamic languages. But it's like parameterized types as a useful feature for everyday use as a code generation tactic. And one of the reasons we want to do this, besides list of int, is list of complex. We are not going to put in a new letter of the alphabet for a prefix for every single new primitive type we want to have, right? That would be impossible. There's only 50 code points left. And in any case, I think we've overused those bytes. All right, so how's it really going to work? I'm not here to tell you that today. As Brian has said, we are experimenting vigorously. There are several different ways it could work. Maybe the letter V is really the letter A because we're secretly putting these things under value-based objects. That'd be kind of interesting. For our own sanity, we prefer to make a distinction explicitly. But maybe some implementation exigency will force us to use A's in the end. I don't know. Do we use type prefixes? Do we use some sort of a bytecode annotation mechanism, which the answer to that is no, because it's too fragile? Do we use some sort of dependent type token mechanism? Don't know. We're figuring it out. It's gonna be fun. So, but the any generics and the value types are driving this investigation, obviously. But it's going to end up with a simpler, and hopefully with a simpler bytecode set. If not, the alternative is we end up with a more complicated bytecode set, and it's already, frankly, complicated enough. Static typing is good. I already said we're not necessarily doing the Lisp Smalltalk type things. What we're doing here, though, should allow an untyped type to exist, like .NET's type dynamic, and maybe several versions of that. So here are the simplifications you get when you remove those prefixes. That's pretty good. Empty opcode maps are good for our world. Let's keep those code points. Slot pairs, Brian already covered that. For arrays, let's talk about arrays. What about the prefixes on those arrays? An AA load is not really the same thing as an A load at all, even though they differ just by one letter. Let's just say, as Brian said, that we need a top type for arrays. So a generic A load, a VA load, would be one which would invoke an interface to get, if necessary, to get an element. And again, with strong typing, so the interface would know whether it's getting an array of doubles or an array of ints or whatever. Again, compare with the scheme move of taking what appears to be a primitive, if then else, and turning it into a library call or small talk. What appears to be a primitive array reference instruction, really under the covers, can be viewed as just an array, an interface call on the array. Here, for concreteness sake, is I've been prototyping on this a little bit, and here's an example of the sort of array interface that I'm writing. This one in particular has 2 parameters, and I don't know what an ordinal is yet, so don't ask me. That's just slideware. But the basic idea is you parameterize over both the index type and the element type, and then everything falls out. And there's a long list of methods. It's a fairly rich type. In particular, you get to import versions of all of the Java util arrays functions. So there's arrays.toString, which everyone in the room has used, I hope. And here it is as its own method. And can it be the toString method? Oh, I wish, but that's a compatibility question that I don't want to solve right now. So in order to make this particular move work, we want to give classic arrays new interface supertypes, right? Sounds good. All that boilerplate above works. I don't know how to spell it exactly. This is early days, but it's either array of int comma e or classic array of e, whatever. What's more difficult is perhaps also we should have the hardwired VM type, the one which is a concrete array, classic array type now, which is the bracket I, for example. Perhaps that should become internally an interface. Oh my gosh, why would you do that? You're going to kill performance. Well, maybe it's useful on balance for array operations to become polymorphic. So like if you have code which is jam-packed with AA loads or IA stores, maybe you want that to work on new library type arrays, right? Like a blocked array or a frozen array or an off-heap array. There's several different kinds of arrays that are natural in this kind of context. Existing array code like sort can become generic, and we can do the specialization trick, right? So we get something like templates out of it. And also we would allow legacy APIs which talk about arrays to talk about new kinds of arrays as well. So there are many Java APIs which talk about arrays which will never change. But maybe it would be worthwhile to replace the kind of array that they return, like have it be non-mutable, frozen arrays, right? Frozen arrays are not necessarily a new class, a new implementation, but it falls out of this move also. The risk, of course, is that we don't want to drop any optimization on classic arrays at all. Classic arrays are bad, but we can't live without them, right? They're not good enough, but getting rid of them would be the wrong move. But we've had some very interesting experiments with optimizing code which works like arrays, like the array mismatch adventure. We can see that the VM is able to optimize that kind of code as well as it can work with plain arrays. So it's hopeful that we might be able to do this. Here's a snippet from some proof of concept work. You can see here I'm grabbing a string. I'm calling on array a freeze operation, and then that's a string array, and I'm asking, are you array equals to your original copy, and it's going to be true. Here's a call of get element. Here's a call of as list. That one doesn't work because generified lists are a little bit fragile. And then here's array to string being called on a string of a primitive, on an array of primitive ints. So that's like, that's about all that ever works right now, but it's worth a slide. So that would let us empty out the array part of the opcode space for the bytecodes. What else? What about all those primitive functions? Well, let's give them API points. Let's also make interfaces, maybe. This might help us organize things. Let's make interfaces for the primitives. So an integral interface, these opcodes here can become interface calls. Bitwise. By the way, I'm not going to minimize the design problems. How do you axiomatize these things? What guarantees and contracts do you put on? You can go to town on this and write whole books on how to do this right. We don't want to do it wrong. So we're going to take that slow. So there's the simplified opcode space. Can we coalesce new Valhalla value types like complex or 128-bit int with the existing primitives? I hope. That will cause
the complexity associated with primitives to become subsumed by the more regular complexity of value types. That's what I'm hoping will happen. In that case, there could be a net decrease of apparent surface complexity, even if there are dark corners. I do believe that int and long are always going to be special. Every language has ints in it, and there's got to be some very basic reasons for that. Here's another idea which probably isn't so good except in certain cases. We can take all the nominal instructions and replace them by indie. So you could actually have JavaC compile only to indie instructions with very few exceptions. That's kind of cute. It reduces complexity in some sense. It's also fairly heavy. But it can be useful for very specific cases where we don't want to hack the existing invocation modes. Maybe we want to do some flexible bridge matching. Yeah, and indie can help with that.
You already do.
Yeah. All right, here's one that's close to my heart. I don't like special. Invoke special, invoke special is a dumping ground for questionable behaviors, and the most questionable of all is the initialization of a blank object. I call that the new invoke special init dance, and I think it's an evil dance and must be banned. It should become a factory call. There's never any reason for, especially for untrusted out-of-capsule code, to make a blank instance and then the verifier is going to make sure, we hope, that you're going to fill it in right. That should just be inside of a library call. And it should be so overwhelmingly common that the VM should be willing to synthesize those factory methods for you and populate them with the one call to new and invoke special init. I want to be able to deprecate or encapsulate the naked opcodes. They should be private, right? A new opcode should be private to the class that you're making a new of. What this would allow, by the way, not only as a cleanliness move, but as a functionality move, it will allow you to do, in a uniform way, the creation of instances and reified generics and arrays, because any parameter you need to create the object is present in the factory method signature, and then whatever the factory method needs to do internally to create the object of the right size and shape and with parameters, generics, whatever, species, that's private to the factory, and you don't need to specify how untrusted applet code plugs together the reified parameters and the array length and the whatever else, right? You just do it all with a factory method. What a concept. So these are a couple examples, of what pseudocode would look like with the invoke static new dance instead of the new invoke special init dance. Note that there's a reified parameter type being passed here and an array length being passed here. You can't do that trick with the existing dance. Finally, it leads to, what about serialization? It leads to a better story for serialization. Wouldn't it be nice if every serialized type gave one or more factory methods to the serialization framework? And then the serialization framework called a factory method, which then could do whatever was necessary for that type to create the thing. Wouldn't that be more secure and safe? It wouldn't cover every last case of serialization, but it would cover a lot, and it would cover a lot more safely. The reason we have serialization the way it is today, one of the main reasons, is it apes the new invoke special init dance in a completely unsafe and unsecurable way. And it's just a bad dance. It turned into the serialization dance. So better would be to have some kind of a convention for saying, this guy has this serialization factory. That's a lot closer to a factory model, and it's a lot easier to secure and think about. Okay, what else besides bytecodes? Class files are too small. We already talked about this. They're also too large. We talked about that too. If you want to load just one method, a class file is too large. They're too rigid because maybe you want to have extension methods on a class, or maybe you want to load the debug methods later and the hot methods first. So why not do a new class file format? Yay? So I'm imagining a hypothetical tie-dye festival in Portland with all the bikers and their tie-dye, and there'd be more bike shed colors on a class file rewrite than there would be on that festival.
Sounds like a demon's house.
So, okay, Another pet peeve. This is on a level with the new invoke special init dance. Our static dependencies are first come, first serve. When you initialize a static module, you run it CL init the first time you touch it. And is that the same order every time? No. Is it in a rational order every time? No. Does it pick up the right class every time? No. Other than that, it's great. This is why people spend their whole careers doing dependency injection frameworks and so forth. Now, there's an interesting direction of a possible way out here. The hotspot, you may have noticed, now implements getStatic and putStatic as derived. Notice the theme of a derived non-primitive on top of lower primitives. It's actually a non-static field on a class object internally. What if we bring that up to the level of the language? What if we start talking about the object which receives the request for a static value or a static method? Gilad is probably laughing at us all here because he called this 20 years ago. Smalltalk also puts statics on class objects. So we could, here's pseudocode for that. Instead of saying get static of c.x, why don't we say load constant of c.class and then get field of c.x of that thing that we loaded. Now that involves different name resolution rules, so maybe it's an invoke dynamic, right? To follow my own rules. But this reduces all the staticky bytecodes to the non-static friends. It also gives you a framework for talking about more explicitly about what your static dependencies are in a module, which could have benefits. And so maybe we can encapsulate the CL init thing more cleanly as a manageable method on an object instead of as a magic block of code, which you're not sure what it does. Okay, initializations are let's see, we already did this one. I'm going to skip this slide. Hello. No, this is the part I want to say. Another feature of statics is that they have this initialization barrier that turns on the initialization. What we're really trying to get here is a framework for run some configuration code the first time I need it. And when do I need it? Well, right now it's when you first load and initialize a class, but that's not always the right answer of when I first need it. Sometimes you want to get a value computed when you first compile an expression. So now we're talking about constant expressions, which Java has a story for, but it's very limited, but maybe we're going to extend it, I don't know. But what I want to say on this slide is there are multiple early points at which you might want to run once some configuration code to assemble you something, and then that will then feed into the later phases of your program. And those phases could include compile time in Java-C, could include the JLink tool, could include class init time as we conceive of it today, or it could be bootstrap execution time, which is per call site, right? There are all these golden points where wouldn't it be nice to just do that computation once and create something robust and simple and then just plant it where you need it, right? So I think that's what static is trying to be. Let's let it out and let it be what it wants to be. Flux. Flux is a problem. There are whole talks on this. We had a keynote from Rich Hickey a few years ago about why Flux is evil. When your whole world is moving, then you can't say anything about it. That's some Heraclitus said that, I think. In Java, everything is non-final by default. How dumb is that? Well, hindsight's 20/20. There's not even a final way to finalize array contents. Hello. Even final variables are not really final. That you can always change them. It's like what they said about the witch in Narnia. You can always get them back. So what does an optimizer do? Well, an optimizer makes special pleading for his friends, like the method handle inlining rules. And so we wonder why there's so much clicking going on the memory backplane. Things are changing when they shouldn't be changing. One of the side aspects, or the associated aspects of this problem of mutability, is that memory is far away. So there's a cost to changing something even if it's innocuous, and it's not innocuous usually. Cache lines, ideally, if you're going to use your memory because you purchased it, you want to get your full purchase price, you want to use 50% of each kind of bit. If you have 99% of one kind of bit and 1% of the other kind of bit, you're only using 2% of your memory, right? Sort of stands to reason, and that's what Claude Shannon would tell us too if he were here. So you don't want your memory, which includes your cache hierarchy, to be polluted with a bunch of useless zeros. It's usually zeros, right? Usually we don't see pollution with useless ones. So I'm going to blame the zeros. So let's, whatever else we do, and this affects JVM and language design, whatever else we do, let's make sure that cache lines, which are here to stay for apparently for the next 20 years, I would venture to guess, let's make sure that they're full of data, full of random data per random access. And that means pointers are not so good, because pointers are probably got a lot of zeros in them, or ones sometimes, depending on your platform. So what you want to do is you want to make sequential accesses to get lots of high entropy bits every time. The VM violates both of those desirable characteristics by heavy reliance on pointers, because a pointer not only has a lot of 0 bits in it, but also points somewhere else where no one's going to predict that you need to prefetch a cache line. Somehow magically, suddenly you need a cache line way over here, and the memory system has to scramble and get it for you. That's called pointer-dependent load, data-dependent load. Arrays help, but not if it's an array of pointers, because then it's just more pointers and it's worse. The JVM cannot express fundamentally one value containing another. That's our problem. That's what we're working to fix. That's one. It's a high-ticket item. Another problem is side effects causing round-the-world trips through your memory backplane. Thread over here says, I want to change that counter. Thread over here says, I want to change the counter too. And the memory backplane says, oh, will you guys please agree which one of you is going to change this cache line? And instead, it's ping-ponging back and forth. It's actually a subtle problem. The simple answer to the subtle problem is stop changing stuff so much. Make things final by default. So a Java object should be mostly, when you need state, you program with it very intentionally and seriously. But when you don't need state, a Java object should just be a message to the future. Here's some stuff I collected once and a header. And now here's a pointer to it. Somebody else read it and do something about it. Share frozen. Friends share frozen stuff. I can't make a good slogan out of that. But you know what? If you have non-local write-to-read effects, they're so often bugs. And it'd be better to catch it by having an exception on a frozen object rather than have your backplane do something and then a thread far away does something else. So we want to color inside those cache lines and use them as if they were trees which were not a fully renewable resource or something. You want to use a whole cache line for random data and then use another cache line near to it. Because we recognize that cache lines, only when they're clean and shareable can they really transmit data to other CPUs. So you want to have you want to pack the cache line, and then that's just one thread, and you're done, and then you hand it off. So how can we make more data structures in Java that neatly fit into consecutive cache lines with nested values? Well, value types. Also arrays 2.0. Also good boxes. A box which doesn't need to be the same box everywhere, but can be reconstituted locally if necessary. Fused array objects, the stuff that Gil Tene was talking about last year. It also means we also want activation records when we get into the fiber coroutine world. We want those to also have the cache-friendly effect also. I want to put that in here. So pointer-free data structures, we are proudly serving ArrayList event next year, even this year. We also want to be able to do larger primitives. I mean, if you can work in one step with a larger value, that's also a good way of nesting stuff close together. And that means Intel AVX instructions. Yay! We want to work with those types. So we're working actively on ways to box something bigger than a 64-bit primitive into a Java buffer of some sort, and eventually have it lifted into registers and so forth. What else? As mentioned before, if we have fewer pointers, at least the ones that we have, that can matter, like B-tree node indexes. And then fuse strings, as I think I already mentioned. You want strings really to be 1 or 2 cache lines long, and that means packing the tail of payload onto the header of the object. We also want the freezing operation, shutting down future changes on both objects and arrays. So we're moving slowly towards those ideals. There's a concept called larval construction, where you say, I've got this thing that's under construction, it's growing inside of its shell, and we're feeding it the pieces that it needs, and eventually it's going to sprout and wings and fly away, and then it doesn't need to change anymore, right? It can be shared by the world, free publication. Note also, just for the record, that object identity is really a side effect. Having to keep one object identity fixed, even if that object is completely immutable, is a cost, because someone might synchronize on it. That's going to tweak at least the bacon bits in the header, and that counts for all optimizations as a potential side effect. So it's ugly. We want identity-free values that are lock-free, that just have content only. Value-based is what they're called. We want more value-based objects. How much time do I have? I'm coming towards the end. I can skip some motherhood slides, but I do want to talk a little bit about threads, because it's not something we're working on hard right now, but we're going to have to. Java began as a threaded language when other languages weren't cool and all cool and thready. They were hard to program. Java was, for many people, many purposes, the best you could get. But threads use enormous amounts of memory. You can't get away. It's like dragging Jacob Marley's box of chains and boxes and cache boxes behind you. It's with you for eternity if you're in a normal threading model. Also, a technical problem is normal threads can't do SIMD lockstep synchronized execution like the indexed type streaming. Whereas with a very small modification to threading, you could say, start me 1,000,000 threads, run them in lockstep on this vector workload. That would be a reasonable semantics. But you can't do that the way threads are configured today. A thread basically holds on to its resources forever until you kill it. A lighter model would be, let's have an event handler, let's run it wherever is convenient, and let's get rid of its resources when it's done. That's better. You can have millions of those instead of thousands. Cue Ron Pressler's demo from last year. This is more about fibers. I'm going to just skip over it because we've talked about this stuff before in this group in previous years. But we want to be able to do lightweight reactive programming, which means basically reifying stack frames, small groups of stack frames on the heap, and then having them mount onto threads and then dismount as soon as they're not working. You also need some continuation mechanisms. You need tail calls so that one handler can call another handler without dragging the dead handler behind him forever like a mini thread. A tail call means you can leave one frame and enter a new one at the same time. It's an important, you don't always need it, but when you do need it, there's no substitute for it. Good. I think the JVM of 5 to 10 years from now will be routinely running many of its computations out of heap-based frames, not stack-based frames. Okay. What's in the activation record? The one thing I want to point out that's kind of interesting is that an activation record seen apart from a thread is a sequence of bytecode executions. He's also an actor in the Java memory model. In other words, who is it that's doing all these happens before relations and these volatile stores and so forth? It's not really a thread. It's the frames of the thread. And so when you try to talk about frames apart from threads, the Java memory model wants to know when that frame dismounts from a thread and then remounts another thread, because the happens before effects need to follow through from thread A to thread B. We can do this. Right, Ron? Good. Races are bad. Variables are hard to tame. We need confinement models. This is one of my motherhood and apple pie slides. This is an interesting slide, though, here, because I want to say that the hardware people, when Java was first created 20 years ago, it was a little ahead of the hardware. Not every machine had good 64-bit integers, right? Some of them had to be done in software. Now Java is in the reverse position. We are behind the hardware. Our best integer is 64 bits. Their best integer is going to be 512 bits soon, right? So, and do we want these dumb, big, long? Who needs that many numbers, right? We've got 2 to the 64 is enough for anybody, right? You've heard that one before. Well, in fact, there are many good uses, and especially lane-wise vectorization algorithms are really cool on this new hardware. And if they're going to give us all these lane-wise parallel execution units, maybe we should find a way to use them from Java. Maybe. What do you think? So we need flat types that can map to those vector types, and we need some APIs for. Remember, I showed you, just as an armchair exercise, what if we got rid of iadd and ladd and lmul and fneg and all those guys and replaced them by API points? Well, it didn't feel like you gained a lot from that, right? Maybe a certain aesthetic satisfaction. But now what if you want to work with vectors and you suddenly need a suite of add and mul and neg? Gee, maybe we need APIs that can talk about these scalar operations in a flexible way and reify them. Yes, okay. So that's the hidden agenda behind beginning to propose primitive interfaces. We want to put those interfaces in non-trivial hardware-centric places like these vectors. So we're sort of on the cusp of being able to use the var handle-like patterns to put a vector in a box so that we can operate on it and hand it to the Haswell execution units. That's going to be really fun. You can do it. The missing piece there is we need some sort of ASM-like trick for getting to all those crazy instructions. Right now, some very good work from Intel is putting those AVX instructions into primitive loops if they're for loops and they're well conditioned. But we want to have free access just to program, because we love to hack with that stuff, right? We want to be able to play from Java with AVX instructions like you can play today using GCC imintrin.h. If you know what that is, it's fun. If you don't, you should try it. So here's again a piece of slideware sketching what a CPU vector interface might look like, because after all, a Java interface does not make any commitment at all to what the implementation is. And in fact, there might be an underlying hardware vector here, especially if we do the boxing elimination right. We have value-based objects. You see these themes all interoperate and build on each other. If I have the right kinds of containers for 256 and 512-bit vectors, and I have the right interfaces, and I can bind them through, with method handles and unsafe, or did I say unsafe? No, no one said that. Then you can begin to work directly with interfaces like this and have them compile up to real AVX instructions or Spark instructions or ARM, what's it called, Neon? Yes? VFP. VFP. All right, so we've come to the end of all the squirrels. There aren't any left. I've chased them all away. But I want to leave you with a big picture. What do we want in 20 years? I claim, join me, I raise the flag. We want a more uniform model, simpler, less apparent complexity, lots of clever tricks underneath. But we want our objects and our arrays and our values and types to feel more similar to each other than they do today, because we're going to be adding in more special cases. We want them to all feel like they're a related family. We want memory efficiency, as I've gone into in great detail. We want good entropy in all of our cache blocks, good prefetching, less pointer dependencies, better vector instructions. We want to be able to share code and then customize it as needed, as Brian was talking about. We want the customization to be mechanical. We no longer want 9 different versions of arrays.sort, right? Yes. But we don't want templates either, because we don't want eager specialization. We want lazy profile-driven specialization. We want to be in a post-threaded world 20 years from now. I claim there'll be too many processors, and the dinosaur threads. Hopefully, a comet will have killed them. We want interoperability with non-managed languages. Good discussion about that today. And we want it to be broadly useful. We want it to run most modern languages, whatever those modern languages are, including Java 20 years from now. And of course, we want it to run the jars of yesteryear. You know, the 40-year-old jars? The 40-year-old jars, yes. My arithmetic is bad. You know, the jars of yesteryear are just like the COBOL programs running on MVS of yesteryear. They're not going away, and our ecosystem has a nice warm corner by the fireplace for them to sit. And of course, we want it to run blazingly fast. We're in the business of helping programmers use the hardware and enjoy it while they're doing it. So, questions?